This first one is an example of determining the weighted average of a combination of naturally occurring isotopes. And we're working with copper. Copper 63 and copper 65. Now there could be other isotopes, but I assume that they're minor. We're also told that the average atomic mass of copper is 63.55. Atomic mass units. Oh, I should start off by seeing if there are any particular that you want to cover first, so that we don't waste all our time with me talking and then not cover your problems. Are there any in there that gave you particular trouble? Okay. So the question is, what's the approximate natural abundance of this one? So we want, what's the percent composition for that one? First of all, do we have enough information? Well, if we look at the formula for calculating the average atomic mass, there's somebody. That's Sam. Okay. The way we calculate it is do a fractional amount of this weight and a fractional amount of that weight to add them together. So if we said, and of course we know that there's only one isotope that has a whole number and infinite zeros. Carbon 12. So we should have been given exact numbers for this one and this one, but we haven't been. So we have to assume that what they're looking at, this value and that value on a percentage base averaged together. So if we say that X percent, or let's say X fraction, right, instead of percent, then we don't have to deal with 100. And what would that make this one? If those are the only two isotopes, then this one would be 1 minus X, right? Or we could say, oh, let's do it that way. I haven't done it that way before. Let me see if it works. Let's do it this way. If this one is X percent, this will be 100 minus X percent, correct? Okay. So now if we say 63 X, that percent times that value, plus 65 times 100 minus X is equal to this value, 63.55. Okay, now we have an equation in one unknown. We just need to expand it and solve for the X. So this would be 6,500 minus 65X equals that value. Then we combine the X's. If we put the X's over on this side, that's minus 2X, right? Minus 2X. This one and that one combined. And this is equal to 63.55 minus 6,500, correct? So now we just need to say, this is going to be a negative number, 6,500 and 63.55. Is that going to work? I wonder. don't think it's going to work. Do you? No, I don't believe it's going to work. It's going to give us a huge number. So there had to be accounting for the percent in here somewhere. All right. So let me go back to my original tactic. X fraction. That means this is 1 minus x. We do that, and we do this, this. 5, 1 minus x. Yeah, that'll work. Okay. So this is going to be minus 2x is going to be 1.45, correct? Negative 1.45. And then we'll divide negative 1.45 by negative 2. And I get 0.725. So the fractional abundance of 63, if that was the question. Yes. The fractional abundance is 0.725 or 72.5%. And the closest one to that is C, 70%. Okay, so we had to use a little algebra. All right. So let's see what is next on my agenda. Yeah, number 3. Number 3 is kind of a trick question, just to see if you're thinking. The average mass of carbon atom is 12.011. That is the weighted average, right, of all the naturally occurring isotopes. Assuming you were able to pick up only one carbon unit, carbon atom or isotope, the chances that you would randomly get one with a mass of 12.011 is what? 0%. It's a weighted average. It's not real. Okay? I mean, it's not based on a single isotope. It's based on the weighted average. So you would not, the chances that you would find any one isotope with that mass are 0. Or very close to it. Okay? What's the mass of 4 atoms of copper in grams? This is a unit conversion problem. Right? 4 atoms of copper. And we want to convert it to grams. So we need conversion factors. Right? So what conversion factor do we know that will convert to grams? The molar mass. That's the only one I know. So the molar mass would have to be grams per mole, grams on top, moles on the bottom, which is the way we want it. But we're not there yet with this. We got to find out moles from this one. So what's the conversion factor for moles? Avogadro's number. Right? That gets rid of atoms, leaves us with moles. Now we can convert moles to grams. We just need the molar mass of copper, which is, I think I got one close by. Copper, 6355. Okay, so our units are all canceled, leaves us with grams. Oh, the rest is number crunching. And that should leave us with 4.22 times 10 to the minus 22 grams. 4 atoms of copper weigh that much. Okay. Next one takes a little bit more thinking. 6 You have a sample of zinc and a sample of aluminum. Zinc and aluminum. And an equal number of atoms. So the moles of zinc equals the moles of aluminum. Okay? Which of the following statements concerning the masses of the sample is correct? So now we want to compare the mass of zinc to the mass of aluminum if we have equal numbers of atoms. Okay? So first of all, as a general observation, are they going to be different, or are they going to have the same masses? They should be different because you've got equal numbers of atoms, and the atoms don't weigh the same. So zinc weighs 65.38. And aluminum weighs 26.98. Okay? Grams per mole. Right? So if we have equal numbers, let's say for argument's sake, we have 1 mole here. So that means this sample would weigh 65.38, this one would weigh 26.98. Or roughly 27. 27. What's the ratio of 27 to 65? At 54. If it was 2 times, that would be 2 times this is 54, so it's more than twice as much. That sample is more than twice as heavy as this one. Okay, now we can look at our choices. The mass of the zinc sample is more than twice as great as the mass of the aluminum sample. There's your answer. And that's why. Okay. All right. Let's see. Do we need to stop at 7? This is another unit conversion. If you have ammonia, it has a mass of 43.5 grams. How many molecules are there? So you would take I guess I better do it. 43.5 grams of ammonia. And he wants to know how many molecules that is. Well, to go from mass to numbers, you always use the molar mass. So what's the molar mass of ammonia? Well, nitrogen is 14.01, and 3 hydrogens is 3.03. So that's 1704. Divide that into 43.5. It'll give you the number of moles, but we need the number of molecules, right? So the magic number there is Avogadro's number. Okay, so moles cancel, grams cancel, we're left with molecules. So Avogadro's number times that is 3 significant figures, 236. 2.36 times 10 to the 23rd molecules. 2.36 is, oh, wait a minute. What did I do wrong? No, I didn't do anything wrong. I remember that. I had the same problem with my other class. That's the wrong answer. That should be C. Okay, I forgot to change it. Save that. There we go. It's good to work these problems sometimes. I find my own mistakes. That was 7. Let's see. How many moles of hydrogen sulfide are contained in 49.7 gram sample of this gas? That's another unit conversion. I don't think we need to do it. I think you could do that one. 49.7 grams. Convert to moles, you need the molar mass of hydrogen sulfide. Oh, but you do need to know how to write hydrogen sulfide. Like that. Why? Because sulfur comes from the chalcogens, it's a -2 charge. Hydrogen is always a +1 charge, or at least oxidation state. Did we talk about oxidation states? I think we did toward the end. When we were balancing equations. Stoichiometric. Chapter 4. Yeah, I believe we did. Yeah, end of chapter 4. So the oxidation state on hydrogen would be +1, and this is +2, -2. So that's how they balance. They don't balance by charge because that's not an ionic compound. But H2S is hydrogen sulfide. Once you know that, then you can determine the molar mass of hydrogen sulfide and complete the calculation. For which compound does 0.256 mole weigh 12.8 grams? This one is like a Henry Ford problem. So you'd set it up for each one. So you have 0.256 moles of each one. A, B, C, D. And E is none of these. So you'd have that value here, and then you need to convert it to grams and see if it compares to 12.8. Right? So for the first one, you'd need C2H4O. Right? You need 2 carbons. You need 4 hydrogens, 4.04. And 1 oxygen, 16, and that's 4406. Right, you do that for each one. Right, you got CO2, CH3Cl, methyl chloride, is a commonly used solvent in organic chemistry. C2H6. And you'd use the molar mass of each one of these to find out the mass. Right? Then when you got the mass over here, compare it to 12.8. And that'll give you the answer. Okay. I'm trying to save time without losing focus on problems that we really need to do. 11. The key to 11 is you got to know how to write barium sulfate. Right? You know you're going to have barium, sulfite. Yeah, sulfite. So you need to look at the polyatomic ions, right? That list of polyatomics that I gave you. Did I give you a list of that? Yeah, okay. And find out what sulfite is. SO3 with a 2- charge. Barium comes from alkaline earths, it's a 2+ charge, right? So that's it. It balances. One of these, one of those. And then add up the values for barium, sulfur, and 3 oxygens. And that should be E, 217.4 grams per mole. Uh, 13, we're given 6.761 moles. Moles of sodium hydroxide. Yeah, sodium hydroxide is a polyatomic ion. So you just need the molar mass of sodium hydroxide and convert moles to mass. Right? That's simple enough. How about, let's see, is 15 worth stopping at? One molecule of a compound weighs 2.93 10 to the minus 22 grams. The molar mass of the compound. Okay, one molecule of the compound weighs that much. This is a dimensional analysis problem, 2.93 minus 22. And that's grams per what? Per molecule. Okay. And what we want to know is what's the molar mass? So we want to know grams per mole. Right? We need moles on the bottom to be grams per mole. Molecules on the top to cancel molecules. And now that's the magic number. Avogadro. So if you multiply that times that, you get grams per mole because that cancels that. And it should come out to 176 grams per mole. Okay, well, this one's worth stopping at, number 17. Takes a little thinking. See if I can do it. All right, what are we given? A compound is composed of element X and hydrogen. X. And I bet it's hydrogen first. Analysis shows the compound to be 80% X by mass. Okay, 80%. 3 times as many hydrogen atoms as X atoms. So there are 3 times as many hydrogen as there are X. Which element is element X? Right. How do we tell what element we've got? There are only 2 ways. If you know the atomic number, simple. But if you know the atomic mass, the average atomic mass, that usually will tell you what it is also. So we can't get the atomic number from this. I don't see any way. But we might be able to get the atomic mass. All right, so if it's 80% X, what does that make hydrogen? 20%, right? By mass, 20% hydrogen. We couldn't do anything with this because we don't want to know what X is, but we do know what hydrogen is. So let's say we have 100 grams, just like we've done before. If we've got 100 grams of sample, that means we have 20 grams of hydrogen. Okay, now we can convert that to moles. Grams up here, moles down here. No, got it backwards. Grams on the bottom, that's in the numerator, denominator. That'll tell us the number of moles. So hydrogen is 1.01. If we divide 1.01 into 20, we get 19.8. We have 19.8 moles of hydrogen in 100 grams. Okay. This ratio is mole ratio as well as atom ratio. So we've got 3 times as much hydrogen as we do, 3 times as many moles of hydrogen as we do X. So how much X do we have? 3 times 19.8, right? 5.94 times 3. I mean 59.4. Yeah, 59.4 moles of X. Now we've got 80 grams of X, which is represented by 59.4 moles, grams per mole. So we just divide that many grams of X by 59.4 moles of X, and that should be molar mass. Let me try that again. 80, enter. 59.4. 59.4. Well, I'm coming out with 13.5. Let's see, what did I do wrong? Did I do anything wrong? 80% X, 20% hydrogen, 20 grams out of 100. So that means 80 grams of X. Let's see, 1.01 into 20. Let's see if I did that one right. 19.8, okay. And 3 times that, 59.4. Okay, that's right. 80 divided by 59.4. Oh, 13.5. Okay, so that's grams per mole. Is there anyone that comes close to that? $13.5. The only one that's even close is carbon. But we're way off, right? Carbon ought to be like 12.01. All right. I still think I've done something wrong. It's not 100 grams of X. Right? It's 80 grams of X. Yeah, 80 grams of X. 20 grams of H. 19, 3 times that. It's how many moles of X? Three times as many hydrogen atoms as X. So if this is how many hydrogen atoms you have 3 times that. Oh, wait a minute. Anybody see what I did wrong? It's not 3 times as many X. It's 1/3 as many X. Divide by 3. Because this represents 3 times X. Divide by 3. 19.8 divided by 3 is 6.6. 6.6 moles of X. Okay, 6.6 into 80. 12.1 grams per mole. Actually, I was reading the value wrong the way I did it wrong. Right? It really wasn't that number. It was a fraction, or very close to it. It was like 1.3 something. Okay, now we know that's carbon. See how easy it is to make mistakes? 17. Let's see. We need to have enough time for the lab, so I got to shut up by 3 o'clock. Okay. 17. Am I recording? Pretty sure I am. I hope I am. I went through the whole morning lecture and didn't record it. Which compound contains the highest percent by mass of hydrogen? Okay, so this one is another Henry Ford situation. You set up the calculations to be done the same way for each one. Hydrogen chloride, water, H2SO4, H2S, and HF. Oops. Okay. Highest percent by mass. So we know how to calculate percent by mass, don't we? What we need on top is how much hydrogen is in there. Well, this is 1.01. This is 2.02. Two hydrogens, two more, and one more. That's the numerator. The denominator is the numerator plus whatever's left. Chlorine is 35.45 grams per mole. H2, 2.02 plus oxygen, 2.02 plus sulfur, which is 3207, and then 4 oxygens. So that'd be 64. And all of these are times 100 if you want to put it in percent. You really don't have to if you're just comparing one to the next. Sulfur, I said sulfur was 3207. 2.02 plus 32.07, and then 1.01 plus fluorine is 19, I believe. Yeah. Okay, so that calculates the percent composition of hydrogen in each one of these by mass. So you just compare them, and you know what? I think this one might be wrong also. It says water has the highest percent by mass of hydrogen. Let's do the calculations. I may have found another mistake. Okay, 1.01 and then 35.45 plus that, divide. That's 2.77%. Okay, 2.02 and then add 16 to it. Divide that is 11.2%. Maybe it is right. And sulfuric acid, 32.07, 64, 2.06%. Make a liar out of me. 2.02 again, and 32.07 right here. And I get 5.93. And HF, 1.01. Plus, that's 5.05. Okay, I was, no, I was right. 11.2%. Okay, never mind. Number 19. Let's see, what do we got here? A substance contains 35 grams nitrogen, 5.05 grams hydrogen, and 60 grams oxygen. How many grams of hydrogen are there in a 153 gram sample? All right. All you have to do is find out what is the percent composition of hydrogen, and then use that, multiply that times 153. Actually, a fraction would be better. Anybody need to work that one? No, I didn't think so. Need to get on some more challenging problems. This one is challenging. Each molecule of testosterone contains 19 atoms of carbon. 19 atoms of carbon per molecule of testosterone. What we need to do is use that to determine the molar mass of testosterone. So I would do it this way. You've got 19 atoms of carbon per molecule. So what's that in terms of mass units per molecule? Because we got to get the mass somehow. If we say this, one atom has 12.01 atomic mass units per atom, right? Okay, so that's atomic mass units per molecule. Let's see what that is. 19 times 12.01 is 22.82. No, 228.2. That's atomic mass units per molecule. Okay, one thing we learned about the periodic table is those average atomic masses could be interpreted as either atomic mass unit per atom or grams per mole. Well, you can do the same thing for molecules, atomic mass units for molecules, or atomic mass units, grams per mole of those molecules. So this is actually equivalent to 228.2 grams per mole of testosterone. Oops, 228. Let me do that again. Oh, okay. The mass percent of carbon in testosterone is 79.12%. What's the molar mass of testosterone? This is atomic mass units of carbon in the molecule. That needs to be converted to atomic mass units of the molecule. So we need to divide this by 0.7912. 228.2 divided by 0.7912. That's 288.4. Now that's 288.4 atomic mass units of the molecule in the molecule. There we go. Now this is equivalent to 288.4 grams per mole. Okay, everybody see why I had to do that? All right. All right, 24 is, I don't think is an issue. An oxide of iron is Fe3O4. What's the mass percent of iron? We know how to do that. 3 times iron in the numerator, 3 times iron in the denominator, plus 4 times oxygen in the denominator times 100. That's pretty simple. Ammonium chromate contains what percent nitrogen by mass? Here we go again. The trick to this one is to recognize my laser pointer doesn't work on this screen, is to recognize that you've got 2 nitrogens here. there's one in this polyatomic ion, but together they're two. So you have two nitrogens in the numerator. Then you go add the rest of them up. Let's see, a hydrocarbon, which means carbon and hydrogen only, is found to be 85.6% carbon by mass. What's the empirical formula? All right, we can do this one. 30. As long as I get to chapter 4 by 2 o'clock. Yeah, then that'll give us enough time for lab. 85.6% carbon. So how much hydrogen is in that sample? That add up to 100? Okay. So now what do we have to do? We're going to do the empirical formula. We have to assume we have a 100-gram sample. If we have a 100-gram sample, then 85.6 grams of carbon and 14.4 grams of hydrogen. Now we can convert to moles, because the formula, whether it's empirical or molecular formula, is always the ratio of numbers of atoms, or not moles of atoms to one another, not mass. Get rid of the grams, leave the moles on top. Okay, so carbon will be 12.01, hydrogen will be 1.01. All right. 85.6, 12.01 is 7.13 moles of carbon. 14.4 and 1.01 is 14.3 moles of hydrogen. Okay, I think you can see that the ratio there is 2 to 1. For every one hydrogen, carbon, you have 2 hydrogens. So the empirical formula should be this: CH2. Okay. All righty. Let's find a challenging one. The empirical formula of styrene is CH. Its molar mass is 104.1. Okay, do this one. So styrene, as in polystyrene, right, foam, coolers, the cheap coolers, or they blow it into the more expensive coolers between the walls. We know that the empirical formula is CH. So what do we need to do to find the molecular formula? We need that multiplier, right? And that multiplier will tell us that we have 1 and 1, or 2 and 2, or 3 and 3, whatever. So if we do that, then we know that the ratio between that empirical mass and the true molar mass will give us that value. So the empirical mass is 12.01 and 1.01, which is 13.02. And we're given 104.1 grams per mole. So if we divide 13.02 grams per mole into 104, I get 7.995, or 8. So our multiplier is 8. C8, H8. That's styrene. All right, I'm not going to do 33 adipic acid, because we use the same procedure there we did for the answer was CH2. The one right before this. just use exactly the same procedure. You're given so much percent of carbon, oxygen, hydrogen by mass. That's it. That's all there is. And determine the empirical formula. Okay. How about vitamin C? Vitamin C contains carbon, hydrogen, oxygen. You know that it contains 40%, 40.9% carbon, 4.58% hydrogen. How much oxygen is there? Subtract those two from 100, and that's your oxygen. And then you go through the same procedure to find the empirical formula, and you ratio the empirical weight to the actual molecular weight, which is given as 180, and you find out what your multiplier is. And that gives you the answer. Should be C6H8O6. That's vitamin C, or ascorbic acid. How many of the following 36 are true? With what we know now about balancing chemical equations, the number of molecules is conserved. Oh, the number of atoms is conserved for each element. The coefficients for the reactants tell you how much of each reactant you're given. No, it tells you how many moles that you would have in a stoichiometric mixture, but it doesn't tell you how much you're given. Atoms are neither created nor destroyed. That's true. So Roman numeral 3 is still true. Coefficients indicate the mass ratio of the substances. No, it's numbers of moles or molecules are the ratio. The sum of the coefficients on the reactant side equals the sum of the coefficients on the product side. Nope, not necessarily. Whatever it takes to give you the same number of atoms of this element on both sides. And for every element, same relationship. So that means A is the only one that's true. It's just that one, Roman numeral 3. When you balance an equation, we change what? To make the number of atoms on each side of the equation balance. Do you change the subscripts or change the formulas? No. Once you've written the formulas for your reactants and products, you can't touch them except to put coefficients in front of them. All right, so B, coefficients of the compounds. That's the only thing that changes. What's the coefficient of oxygen when the following equation is balanced? All right, so let's balance an equation. 39. We'll probably do 40 also. So I think 40 is a squirrely one. What we'll get started with should be an easy one. Ammonia plus oxygen. All right. And nitrogen dioxide and water. Okay, so I'm going to use the budget method. We got to account for nitrogen, hydrogen, and oxygen. That's it. On this side, we got 1 nitrogen, 3 hydrogens, 2 oxygens. On this side, we have 1 nitrogen, 2 hydrogens, and 3 oxygens. Okay, so we can see this is not balanced. So which one are we going to hold out to the end? That one, because it's an element. If we put a coefficient in front of that, that's the only one that changes. Okay, nitrogens are already balanced. They may not stay that way, but for now, we might as well leave them alone. Hydrogens. Well, hydrogens in one place here and one place there. The thing about it is, this hydrogen is an even number and that was an odd number. So when that happens, one of the tricks that I think I put in that document is cross multiply. So it only occurs in these 2 places, one on either side. So if we put a 3 here and a 2 here, that gives us 2 nitrogens, 6 hydrogens on that side, and 6 hydrogens on this side, and 3, 4, 5 oxygens on that side. Okay. Now let's take care of nitrogen over here. All right. So we have 2 there. That's 2 nitrogens. But now we have 4 and 3 is 7 oxygens. Okay? So we're down to the last one. How do you get 7 out of O2? Use a fraction. If we say 7 halves of O2, that'll give us 7 oxygens, right? Because O2 is like this. Be complete. And if we take a half of that, we're talking about this, times 7. So that gives us 7 oxygens. Now we want to get rid of the fraction. Right? So how do you get rid of a fraction like that? Multiply everything through. This ratio is now fixed. That's accurate. That is the ratio, molar ratio of all reactants and products. It's balanced, but it's not whole numbers. So if we multiply through everything through by 2, 2 times 7 halves is 7, correct? Right. So now this one becomes 4, this one becomes 7, this one becomes 4, and this one becomes 6. So we have 4, we've used that up. 4, 7, 4, 6 are the coefficients. Which one do we need? Oxygen. 7. 7 is the coefficient for oxygen, which is C. Okay? Did I lose anybody? Okay. Let's see. What is the sum of the coefficients for 40? Let's do 40. I got a sneaking suspicion 40 is going to be trouble. NaNH2. NaNH2. NaNO3. NaN3. NaOH, and ammonia. Okay, sum of the coefficients. Let me back up and take a look at this thing. There are no polyatomics that are untouched during the reaction, so we've got to account for each element separately. Sodium here. Nitrogen, hydrogen, sodium, nitrogen, hydrogen, sodium, nitrogen, oxygen. That should be everybody. Okay, on this side we have 2 sodiums. We have 1, 2 nitrogens. We have 2 hydrogens. And we have 3 oxygens. And on this side we have 2 sodiums. We have 4 nitrogens. We have 4 hydrogens. And we have 1 oxygen. All right. The reason I know that this is going to be trouble is that we've got elements in multiple locations. 2 nitrogens here, a nitrogen there, nitrogen there. Hydrogen seems to be fairly well behaved, except it's in 2 places over here and only 1 over there. Oxygen's better. It stays in 1 compound on either side. Okay, there are no elements, so we can't reserve any of those. Sodium's already balanced. Nitrogen's even, hydrogen's even. Oxygen, I'm wondering if we ought to mess with oxygen first. Or nitrogen. You know, this might be one that we could use redox method. No, I guess not. Okay. So where do we start? What if we do the oxygen first, since it's only in one location? Sometimes you just have to start and bulldog your way through it. If I put a 3 here, that makes 3 oxygens. Okay. It also makes 3 plus 3 is 6 hydrogens. Okay. Now I've got 3 sodiums. 4 sodiums, excuse me. 4 sodiums. All right. So look at what has to be balanced now. Hydrogen, oxygen, and nitrogen, and sodium. So what if, so if I put a 3 here, that'll give me 3 plus 1 is 4 sodiums. But what does it do to the others? Okay, 3 plus 1 is 4 nitrogens. That would do it. 3 times oxygen would be 9. That'd mess up the oxygen. So we need to use, maybe we need to do 3 here, because that would give us 3 sodiums plus 1 is 4. But it wouldn't touch the oxygens. See? 3 nitrogens plus 1 is 4 nitrogens. And then hydrogens, 6 hydrogens. There we go. That was really not obvious, the best way to approach it. I can't give you a method. You just have to say, what if? But I'm wondering if a redox method might work on this one. Let's see if there's any change. Well, sodium's the same, both sides, oxidation state. Nitrogen, that would be plus 1 and plus 3. So this would be minus 3. This would be minus 3. No, this would be, that'd be a fractional. Okay. I don't think it would help us. Okay, that was 40. I think there is one in here where you use the redox method. I believe it's toward the end. So let's, when this equation is balanced, all right, 43 is fairly simple to balance, except notice that it's combustion of a hydrocarbon. Anytime we combust a hydrocarbon, to balance the equation, you have to use the fraction trick. Except for one, methane, CH4. You don't have to use the fraction trick for that one. But for the rest of them, you always have to use the fraction trick. If you've got a hydrocarbon combusted to yield carbon dioxide water. I don't know why, but well, I do know why. It's math. So I'm not going to stop at that one. Just know that you have to use the fraction trick. Number 44, this reaction, balancing this reaction, requires that you write out the chemical formulas and the reaction equation from a word problem. So I'll set it up for you. 44, sodium carbonate. Sodium carbonate. Why do I have 2 here? Because that's a 2 minus charge. That's a 1 plus charge. Reacted with hydrochloric acid, HCl. And what does it yield? Sodium chloride, sodium plus chlorine, plus carbonic acid. Well, actually, that decomposes into water and carbon dioxide. Okay? So once you've written these things, then it's fairly easy to balance after that. The trick is getting these compounds written correctly. If they're not written correctly, you'll never balance it. All right. So 45 is kind of like that first one we did with the solids, liquids, and gases. You have to read the problem and say, what is it asking for? If the equation is 2A plus B yields C, what's the question? Which of the following figures best illustrates a stoichiometric ratio of A and B? That means that only. That's the stoichiometric ratio. So if it's got C in it, that can't be. So number 4, Roman numeral 4, you just throw it out. It doesn't fit the problem at all. So the rest of them, you want twice as much A as you have B. So you count them up. Right? Which one satisfies? Only one. Roman numeral 1 has a ratio of 2 to 1, A to B. The rest of them don't. All right. Stoichiometry for 46. If you've got this potassium chlorate, and all you have to do is heat it up, and it leaves behind potassium chloride and evolves oxygen. That's a very simple experiment. Some chemistry instructors use it. How many moles of oxygen are formed? So it's important to recognize that what you have to do is, before you can find out how many moles of oxygen you have, you got to find out how many moles of potassium chlorate you have. Because you can't go anywhere in an equation with mass. It doesn't work that way. It's got to be moles. So you need 7.11 grams of potassium chlorate, and you need molar mass of potassium chlorate to find out how many moles it is. Then where do you go? You look for the coefficient ratios. Right, now that you have moles of potassium chlorate, then you use the ratio of 3 oxygens to 2 potassium chlorates, 1.5 times that value, and that's why you get moles of oxygen. Should be 0.0870. Okay. How many grams of calcium nitrate can be produced by reacting HNO3 with 6.33 grams of calcium hydroxide? What type of reaction is this? By reacting HNO3 and calcium hydroxide yields what? Calcium nitrate. What else is there? You have to recognize this is an acid-base reaction. There's your acid, there's your base. When you react an acid and a base, you get a salt, calcium nitrate. What's left over? Hydrogen and hydroxide. Water. Okay? You have to know that. Otherwise, you can't balance the equation. Right? So how do we balance this equation? Well, we've got one calcium, that's fine. We've got 2 nitrates. 2 nitrates. Now you have 2 hydrogens, 4 hydrogens, and 2 oxygens. 4 hydrogens and 2 oxygens. Now it's balanced. And you can proceed with the question. 6.33 grams of calcium hydroxide. And it asks you how many grams of this one are produced. So you know what to do next. Convert to moles, change moles of that to moles of this, which will be equal, right? 1 to 1. then change it back to grams. Okay? All right. Well, I'll be getting close to chapter 4 by now. I'm going to skip that one. I was looking for one with limiting reactants. All right, 58. For 58, I do need to get into chapter 4 before too long. But I would say that 58, where you have, this is your balanced equation, right? It's giving you the coefficients. And you have 5.95 grams of silver nitrate reacted with excess barium chloride. You have to assume that. To give you silver chloride, what's the percent yield? Percent yield is going to be, this one is the actual value. So you need the theoretical value. You've got to take this in the balanced equation, find out how many moles of that, then moles of this, which would be equal, then reconvert that to mass and use that in the denominator here. And then do your calculation, and that'll give you 63% efficiency. Okay? All right. For 59, you're given a balanced equation, but you're also given exact amounts of 1.2 moles of methane, one reactant, and 1.11 moles of chlorine. Right? I think we can knock this one out pretty quick. All right, so we have methane, chlorine, and yields carbon tetrachloride plus HCl. And it's a gas. Okay, you're given 1.20 moles of methane and 1.11 moles of chlorine. What mass of this do you end up with? Whenever you're given exact amounts of reactants, one of them is going to run out. It's rare that you're given a stoichiometric mixture. So look at this. Since they're already in moles, if you have 1 mole of this, how many moles of that are you going to need? 4. If you have 1.2 moles of this, you're going to need 4.8 moles of that. Right? And you only got 1 point. So this one is the limiting. So use that one and the coefficients to find out how many moles of this. Right? So divide 4 into that one, it gives you the moles of that. Then use the molar mass and convert to grams. You got your answer. All right. 61. I'd like to do 61. If you're given the following reaction, that's C2H6 is ethane, 2 ethane plus oxygen, that's a combustion reaction. It's also a redox reaction. Yields water and carbon dioxide. If we have equal masses of C2H6 and O2, there's no limiting reactant. Well, I guess I'm going to have to do it the long way. 2 C2H6 plus oxygen, 7 oxygens, yields carbon dioxide and water, 6 and 4. Oops. wrote them backwards. 4 and 6. Okay, if you have equal masses of carbon of C2H6 and O2, so this mass is equal to that mass. There's no limiting reactant, which means you have a stoichiometric mixture of 7 oxygens for every 2 C2H6. So what's the molar mass of C2H6? Right. 12.01 times 2. And then 6.06 for the hydrogens. So that's 30.08. 30.08 grams per mole. Oxygen is 32 grams per mole. Okay, if you have equal masses, how many moles do you have? Well, roughly equal moles, don't you? Not exactly, but pretty close, 30 and 32. So that would be 2 to 2 or 7 to 7. You don't have that. This is not a stoichiometric mixture to have equal masses. Does everybody see that? Okay. So A is wrong. B, if we have an equal number of molecules of C2H6 and O2, there's no limiting reactant. Equal number of molecules. That says that the ratio is 2 to 2 or 7 to 7 or something like that. It's not. So B is false. C, if we have more mass of C2H6 than we do of O2, then if we have more mass of C2H6, then O2 must be limiting. All right. So if we have more mass than what? I was saying more mass than O2. Say, is this one bigger than that one? This one is still limiting because it takes 7 times as much. So O2 is limiting. And that's our answer. We found our answer already. All right. I'm gonna skip that one. St. Hume's agent is the actual mass. Okay. 64 is like that last problem that we did in, let's see, was it chapter 3? Or was it 4? It's the last one in 3. We had phosphorus and fluorine. And we said, what mass of phosphorus would be required to guarantee you a certain amount of PF3? Or is it PF4? With a certain percentage of yield. So we have that here. We have the yield that we're given for this reaction. We have what actual mass of hydrogen is produced when this many grams of nitrogen with 4 and 4.45 hydrogen. So you've got to find out which one's limiting, right? And then once you find the limiting reactant, you can find out the mass of N2H4. Theoretical, but if the percent yield is 82%, then you multiply 0.82 times that value, and that gives you your answer. Okay, all right. Tetraphosphorus decoxide, molar mass of that, used 4 phosphorus and 10 oxygens. Add them up. Greatest number of moles of carbon atoms. In this one, you have to find out first for each one of those, using Henry Ford again, 69. You say, how how many moles of compound first is each one of those grams. Then once you find the moles of compound, you ratio that to the number of moles of carbon atoms per moles of compound. So the first one will be 4 to 1. The second will be 2 to 1, and 1 to 1 for C, and 6 to 1 for D. And that's how you find out how many moles of carbon atoms. Because if you just find the moles of the compound, you're only part of the way there. We're not going to do 70. All right, that's a empirical and molecular formula problem. 71 is calculate the average atomic mass for iron if you have certain percentages of those isotopes. And in this case, you're actually given the values, the actual values for the isotopes here. So you don't have to use these numbers, you use those numbers, right? And sequence this one, that one's that one, that one's that one. And just do that calculation. All right. This one just tests to see if you can derive the empirical formula from these molecular pictures, right? That first one is 6 carbons and 6 hydrogens. So the ratio is 1 to 1, CH. This one is C2H4 is the molecular formula, so CH2 is the empirical formula. You just do that for all of them. Find out what the molecular formula is and then reduce it by dividing through by some whole number. That'll give you the simplest ratio. Okay, now we're in chapter 4. All right. How much time do I have? 40 minutes. Okay. An unknown substance dissolves readily in water, but not in benzene. Molecules of what type are present in the substance? Remember, like dissolves like. What that means is polar dissolves polar, and nonpolar dissolves nonpolar. So if your substance dissolves readily in water, but not benzene, which is a nonpolar solvent, then everything in the substance, the solute that you're putting in solution, has to be polar. That's why the answer is B. Which one of these is not a strong base? Okay. We didn't hammer this one too hard during the lecture. Strong bases are hydroxides of alkali metals or alkaline earths. Right? Calcium is an alkaline earth, so that's a strong base. Potassium is an alkali metal, that's a strong base. Lithium is an alkali metal, that's a strong base. And strontium is an alkaline earth, that's a strong base. The only one that's not a strong base is ammonia. Right? And we'll work with ammonia again later. But that gives you the logic and the answer. Which one is paired incorrectly? H2SO4. Is that a strong acid? Sulfuric acid. HNO3, nitric acid. That's a strong acid. That's paired. That's wrong. You can stop there because you don't have any squirrely ones in there, like none of the above, 2 of the above, so forth. So you found your answer. HNO3 is a strong acid, not a weak acid. We didn't cover this one either. The man who discovered the essential nature of acids must be in your textbook. Through solution conductivity studies was Arrhenius. Arrhenius discovered the essential nature of acids. And when we get to a discussion of acids and bases, oh, wait a minute, that's not this semester, is it? I think that's next semester, acids and bases. We'll talk about Arrhenius' definition of acids and bases. But for now, he's the one who started the ball rolling with acids and bases on a theoretical basis. So if you have 16.4 gram sample of HF and you dissolve it in water, what is it before you put it in water? It's hydrogen fluoride. When you put it in water, it's hydrofluoric acid. And concentrated hydrofluoric acid is extremely dangerous. If you get a drop of that stuff, and I think it's in the neighborhood of 35 or 37% concentration, I've used it in that, it's concentrated. If you drip that on your hand, it will go through and keep eating until it goes out the other side. It's a reaction with mostly the calcium in your system. So it'll go right through your bone. So we always double glove when we use that one. But sometimes that's the only thing that will work when you're dealing with soils like I was, and you're trying to dissolve the silicates. Silicon fluoride is a soluble compound. So you have HF in your digesting matrix to get the silicates. And there's no other choice. Okay, so what is it asking for? What's the molar concentration? So what do you need for the molar concentration of anything? By definition, molarity is moles of the solute per liter of the solution. So we find that dissolved in water to give 2 times 10 to the second milliliters. Right? 2 times 10 to the second milliliters is what? How many liters is that? Oops, too many zeros. Only 2 significant figures. There we go. Liters, right? That's 200 milliliters, which is 0.2 liters. Okay, and moles. Well, moles you have to calculate from 16.4 grams of HF. So you need the molar mass of HF. Right? So 19 for F and 1.01, so it's 20.01. Okay, divide that out and then divide it by this one. That's your molarity. Let's see. What mass of calcium chloride is needed to prepare 1.49 molar solution, and the final volume is 3.950 liters. And go back to the definition. Molarity is moles per liter. So we got liters, 3.950 liters, but we don't have the mass. In fact, we're looking for the mass. So what you do is, if this is the definition, and you're looking for a mass of calcium chloride, you got to get there from the moles. So moles is equal to molarity times volume. You multiply molarity times volume, which is given to you. That gives you the moles of calcium chloride, and then you use its molar mass to convert to mass. That's very practical. We used to do that kind of thing all the time, preparing solutions. Only we didn't use odd volumes like 3.95 liters. It was usually whatever volumetric flask we had, either 1 liter or 2 liters. We actually had a 4-liter volumetric flask. And we prepare concentrated solution. One of them was calcium chloride, but it had something else in it too. And we prepare a concentrated solution, so then when we got ready to do our extractions, soil extractions, then we would dilute it down using that formula, M1V1 equals M2V2. Use that formula and dilute it down to our working solution. What mass of solute is 256 milliliters of 0.838 molar ammonium chloride? Okay, two things here. You got to find the moles, but it's 0.256 liters times molarity gives you moles of ammonium chloride. Then you have to know the formula of ammonium chloride because you got to know the molar mass, right? NH4Cl, because ammonium is +1, Cl is -1. You only need one of each. And that will give you the mass. 74.28 gram sample of barium hydroxide is dissolved in enough water to make 2.45 liters solution. How many milliliters of this solution must be diluted with water in order to make 1 liter of 0.1 molar barium hydroxide? That's the type of problem I just described to you. Yeah. One before that, where we make up a concentrated solution, which is what you're doing first, with that many grams of barium hydroxide in 2.45 liters of solution. So you find out what is the concentrated molarity, right? And then you put it in your, once you find the concentrated molarity, and then you know your target, and you know the volume, diluted, diluted. You know these, you know these, you know these. You calculated this one. Now you're looking for this one. Okay, how many milliliters, right? Okay. 18 is another dilution problem. The key to doing dilution problems is set up a table and put values in here for concentrated, concentrated, dilute, dilute. So you get them in the right place when you stick them in your formula. If you don't do that, then you're liable to get crossed. And put this one in that one and that one in this one, and then you're all is lost. All right, let's see. What type of reactions are these? Number 28. Well, let's see. What kind of reaction is that? ZnBr2 aqueous. It's an ionic compound in solution. Silver nitrate aqueous. Okay. Yields zinc nitrate aqueous and silver bromide solid. What kind of reaction is that? Precipitation. You've got two solutions you put together, and when they react, boom, you get a solid dropping out. That's a precipitation reaction. The next one is a similar type, right? You've got a solution and a solution put together, you end up with a solid. Okay, those are precipitation reactions. They're a subset of, well, actually, yeah. The same thing as a double replacement. You just swap partners, swap cations. So that's why the answer is C. It's not an acid base and it's not an oxidation reduction. You know it's not an oxidation reduction because all you have to do is look at the, since these are ions, well, these are polyatomic, so you have to break those down, right? Zinc is a +2 here and a +2 there. Silver is a +1 and a +1. Bromine is a -1, and it's still a -1. And then nitrate didn't change at all, right? So it can't be redox. And if you got one of them disqualified as a redox, then you can't answer that as a redox in the answer, because if there's only one of them, then it doesn't fit both. Okay, 29. All of the following reactions can be classified as what? Remember that rule, that trick I gave you? If you've got an element on one side, it's in a compound on this side, what kind of reaction is it? Redox. Oxidation reduction, yeah, every time. Here you got a compound, element, element. Here, that's a hydrocarbon, and with oxygen, it's a combustion. And all combustion reactions are redox. Well, plus oxygen's an element on one side, it's in a compound on the other, so you can use that rule too. but it's oxidation reduction reaction. Now, one of your selections here is also combustion reaction, but only one of them is combustion. So you can't say that about all of them. Combustion has to have free oxygen, elemental oxygen. So that's why only A is correct. Okay, which of the following salts is insoluble in water? So how do you use your chart? You go look for the cation across the top, right? Sodium, down the left-hand side of your chart as your anions. You follow to where they meet and look, see, is it grayed out or is it a clear square? And sodium sulfide is clear square. Potassium carbonate is soluble. Lead nitrate is soluble. Calcium chloride, they're all soluble, right? Because I'm thinking of the rules rather than using this thing. But you can use this and get the same answer. They're all soluble. That's why E is the answer. Let's see. Okay. Consider the aqueous solution of calcium nitrate and sodium phosphate. 37. Calcium nitrate and sodium phosphate. Okay. And the question is, what is the formula of the solid that forms from this reaction? So you don't really have to balance the reaction. You just have to know what are the cations and anions that can interact. So if we interact sodium with nitrate, what do you get? You get a soluble salt. Right? So they're spectators. So what do you have left? You have calcium and phosphate. Calcium and phosphate. So we need 3 here and 2 there. So calcium 3, phosphate 2 is the formula. And that is number C, or letter C. Okay. $38, the balanced, oh, okay. 38, 39, and 40. We write out the molecular equation and balance it, and then look for a match with 38. So I guess we better do this one. Let's see. The word problem says aqueous solution of barium chloride. Right? Barium is an alkaline earth, chlorine is an halogen, so you need two 1 minuses to balance a 1 2 plus. That reacts with silver nitrate. Right. Silver is one of those with a single charge. It's only a +1. Nitrate. That's aqueous. Then what do you get? Well, barium swaps places with silver. So silver chloride +1 - 1 is insoluble. And then barium nitrate is aqueous. And this is 2. Because barium is 2 plus, nitrate is -1. Okay, now we need to balance it. We could lay out our budget. And since we got nitrate on both sides, we can use it as a balancing unit. But these type of reactions are really easy to balance. We got 1 barium on either side. We got 2 chlorines here, only 1 there. Like that. Now we need 2 silvers. All right, so 2 silvers, 2 nitrates, 2 nitrates, 1 barium, 1 barium. 2 silvers and 2 chlorines. We're balanced. That was really simple. Okay, so which one of these species matches 38? And notice it's got coefficients. So we got to find the one that has the right coefficient also. Right? Silver chloride. Nope, because it has 2 in front of it. B. That one works. Silver chloride, solid. Okay. Now, complete ionic equation. So we've got, let me start way over here. Barium 2 plus 2 chlorides, right, because of that subscript. 2 silvers and 2 nitrates. That's just the reactants. Now, the product, we can't touch this one because it's a solid. We have to leave it just like it is. Now we have barium 2 plus in solution still, and 2 nitrates because of that 2 subscript. That's the complete ionic equation. And let's see which one matches. No, not 2 bariums. How about 1 chloride? Nope, 2 chlorides. 2 silvers. 2 silvers here. That's the one. Aqueous 2 silvers. Okay. Now, the last one is the net ionic equation. So how do you get from complete to net? You cross out the spectators. Right? So we know that this one comes from that one and this one. So barium's a spectator, nitrate's a spectator. So now we have 2 of these, 2 of these, and 2 of these, but that's not the simplest. Right? So we want to reduce that to 1, 1, and 1. Now we have 1 silver, 1 chloride yields 1 silver chloride, solid. Now we look and see what's available. Silver aqueous, yep, there it is. Barium's not there, nitrate's not there, hydrogen was never there, and silver chloride aqueous doesn't exist. That would be in solution, and we know it's a solid. All right. I'm going to skip those. What mass of sodium hydroxide is required to react exactly with 25 milliliters? Okay, we probably ought to do this one too. Okay, I think I got enough time. The next one coming up is a titration. $50. The reason I want to do this one is because we're going to do a titration later on in order to determine the molar mass of citric acid. We have to do a titration to do that. So what mass of sodium hydroxide reacts with sulfuric acid? So H2SO4 reacts with sodium hydroxide, aqueous, and yields what? Sodium sulfate, and that's soluble, plus what? Well, we got hydrogen and OH. Water. That's true for any acid-base reaction. Acid plus base yields salt plus water. And that technically that's a salt. Anytime you combine the cation with the anion from an acid base, you get a salt. It's not always sodium chloride. That's table salt, but this is a salt in chemical terms. Now we need to balance it, right? We've got 1 sulfate, oh, 2 sodiums, 2 sodiums. That gives you 2 hydroxyls and 2 hydrogens, which means 1, 2, 3, 4 hydrogens and 2 oxygens. So now we're balanced. Now we can answer the question. What mass of NaOH is required to react exactly with 25 milliliters oops, I added an extra significant figure. There we go. And at 2.7 molar. All right. So if we multiply 27 by 25, what do we get? Millimoles. 2.7. So I get 67.5 millimoles of H2SO4. Now we need, how much sodium hydroxide is that? Well, for every one sulfuric acid, we get 2 sodium hydroxide. So that's 2 times that is 135 millimoles of sodium hydroxide. Okay, we can't use that to convert to mass, right? We need moles. So how many moles is that? Remember the trick? This prefix, milli. Milli is 10 to the minus 3. So 135 times 10 to the minus 3 moles of NaOH. Now we can convert that to mass. We just need the molar mass of sodium hydroxide. Okay, sodium is 23. Yeah, 23. 23. Oxygen is 16. And hydrogen is 1.01. So that's 1, 0, 6, 9, 10, 40. 40.01 times 135 times 10 to the minus 3. And let's see. 40.01. I get 5.4. How many significant figures? 2. 5.4 grams of sodium hydroxide. Okay? That was sort of a titration, isn't it? Not what I was expecting. But it illustrates the point that in this reaction, we had a base that delivered 1 hydroxyl, but an acid that delivered 2 hydrogens. So it only took half as much sulfuric acid to neutralize a certain amount of sodium hydroxide because it delivered 2 hydrogens per molecule. So that ratio is 2 to 1, rather than, I think the example we used earlier was hydrochloric acid and sodium hydroxide. Those are 1 to 1. All right. Okay, can you do oxidation states? Let's see. We'll do 52. Okay, which nitrogen has an oxidation state of +4? Okay, we got nitric acid, NO2. N2O and NH4Cl. And NaNO2. Okay, remember how to find oxidation states. Got to use the rules to nail down everything but the one you're looking for. So oxygen's always -2, hydrogen's +1. That means this is 6 minuses. And this is a +1. So that's a -5. That means this nitrogen has to be a +5 to balance that -5. Okay. This one's -2, which means -4. So this one has to be a +4. There's our answer. B is the answer. But you do the same thing. They're all neutral. So they have to add up to 0. Let's do one where we have an ion. How about 53? IO3-. That's a polyatomic ion. iodate. All right? So this oxygen is -2 times 3 is -6. But we got to hold out one of those minuses for that charge. So you only have to balance -5 with that iodine. Okay? So in this polyatomic ion, iodine is not -1. It's a halogen. But in this combination, it has an oxidation state of +5. And if you look on your periodic table, yeah, +5 is one of the possibilities. So you got a list of +1, -1, +1, +5, +7 are possible for iodine. Those are oxidation states. The first one is usually a charge if it's an ionic compound, but the rest of them are usually oxidation states. All right. Which of the following is not true? I'm going to skip that one. In this reaction, which species is oxidized? Remember the acronym oil rig? Oxidation is loss. Which one actually loses electrons? Well, the calcium, this is what oxidation state? 0. It's an element. That's 0. Over here, it's 2+ and 2- for oxygen. So which one lost? Calcium. Calcium lost. Calcium was oxidized in that process, which means oxygen had to be reduced. They always go in pairs. Let's see. In this reaction, chlorine gas is what? Reducing agent, oxidizing agent, oxidized electron donor. Let's draw this one out. Let's see. Cesium, chlorine, cesium chloride, right? Oh, no. There we go. And there are 2 of these. Okay, so what happens? Well, this one's 0 and that one's 0 because they're elements. Over here, this one's -1, this one's +1. So the wait a minute, ask us for chlorine. What happens to chlorine? It gains an electron. It's reduced. Is that one of our, that's not one of our choices. So what do we also call something that's been reduced? Is the oxidizing agent. It causes the oxidation of something else by being reduced itself. So that's why the answer is B. It's the oxidizing agent. Let's see. 63 is too easy. Let's do one that's a little more difficult. Spectators. Precipitate formed, you can do that one. Nitrogen with the highest oxidation state, right, we've been that route. Which of the following does iodine have the lowest oxidation state? No, we don't need that one. Fill in the blanks. Okay, here we go. What is that compound? You may not recognize it. That's nitroglycerin. That's why it's so explosive. Right? When you detonate this stuff, actually you only have to jiggle it a little bit, it'll go off if it's in liquid form. And it generates nitrogen gas, carbon dioxide gas, water, vapor, and oxygen gas. And that's where the explosive force comes from. Let's see, I've only got 7 minutes. Do I want to do that one, or let's do 78. Right, we could do this one, and it's not that difficult. But this one, I think that's the last one. Yeah, this one uses, we're going to use the redox method to balance this one, 78. That should take us to the end of the lecture, or review session, 78. Okay. So we're starting off with Ki and HNO3. Let's see, let's do Ki plus HNO3 yields KNO3 plus NO plus I2 plus water. Okay. So how do we know to use the redox method? Well, you look at what you've got here and you see that iodine's in a compound and here it's an element. So we know it's a redox. Now, there's a chance you could bulldog your way through it and balance it without redox. But believe me, it's much simpler if you do the redox first and then finish it off from there with the standard procedure. Okay, so this one is a +1, this one's a -1, that's a plus, this is a -2. So that's -6 plus 1 is -5, so this is +5. That nitrogen is +5. All right. This one's going to be the same thing, right? Because the nitrate didn't change from one side to the other. But this one, -2, this is +2. So that nitrogen changed. This nitrogen went to here to a +2. This one's 0. And water and that didn't change. The oxygen didn't change from either side. So what are the redox species? Iodine. What happened? It went from a -1 to a 0. It lost electrons. It was oxidized. So we have a loss of 1 electron per iodine. Okay. The other one is one of these nitrogens went to here. And that gained 3 electrons per nitrogen. Okay? Now, we just need to balance the electrons. So in order to, what we've got here is if we've got 2 iodines there. If we put 2 iodines here, then we're still not balanced, right? 2 to 3. So if we say 2 times this one and 3 times that one, we should be able to balance. So we say 2 times this one, that's 6 electrons. So we say 2 here, and that's 2 nitrogens there. Oh, that's okay. Because there's 2 nitrogens here, and there's 1 there and 1 there. Oh, wait a minute, we can't do that. Can we? No, because both of them have to go to here to give you those electrons. We got to do 2. Does everybody see that? Okay. Now we need 6 electrons here, so we've got to by 3. So if we do 3 here and 6 here, that's 6 iodines, 6 iodines. 2 times 3 is 6 times 2 minus equals 6 electrons. And you can check your electrons. We only had 1 electron lost 6 times. So that's where we start for the rest of it. We've got the electrons balanced. So now you go in and you say, let's clean it up. This one's 6. That's 2. That. Okay. Now we can tally 6 potassiums. We had iodine, 6 iodines. We had hydrogens, 2 hydrogens. We can't keep nitrates as a balancing unit because it goes this way one way and that way the other. So we've got to say nitrogens. So how many nitrogens do we have? We have 2. Yeah, 2 nitrogens and 6 oxygens. On this side, we have 1 potassium. We have iodines, 6 iodines. We have 2 hydrogens. Yep, 2 hydrogens. Nitrogens, we have 1, 2, 3. 3 nitrogens. And we have 1, 2, 3, 4, 5, 6 oxygens. Okay. Let's see. If we do 6 potassiums here, that balances that one. What does that do to the rest of them? Okay. 6 nitrogens, 6, 7, 8. That makes 8 nitrogens. And it makes 3 times 6 is 18, 19, 20, 21 oxygens. Okay. How about nitrogens on this side? So if we need 8 nitrogens over here, I got to put an 8, don't I? Yeah. So that makes 8 hydrogens. And it makes 8 nitrogens. And it makes 3 times 8 is 24 oxygens. Okay. Now go back to hydrogens. I need 8 hydrogens. Right? That's the only place there's a hydrogen. So that's 8 hydrogens. Oops, sorry. 8 hydrogens. And 4 oxygens plus 4, 5, 6. And 6 plus 18 is 24, right? There you go. It's balanced. that was a tall order. Okay. And if you try to do this brute force, maybe you can do it, maybe you can't. But I found that doing the redox first gets you on the right track quicker. Let's get the electrons balanced out, and then we go for the atoms. Okay. So you might need to take a break before we do a lab.